We possess this incredible, almost restless capacity to explore. It's just hardwired into us, right? But as we sit here today looking up at the sky, we have to ask ourselves, how far does our technological reach actually extend right now? We are living in an absolute golden age of space exploration, where yesterday's science fiction is rapidly becoming today's engineering reality. We're literally preparing to leave Earth in ways we never have before.
So, how far can humanity actually reach? I really want you to hold on to that cinematic existential question. Think of this explainer as a virtual journey. We're going to start with our feet firmly planted on our home planet, and step by step, we'll travel outward, past our atmosphere, past our nearest celestial neighbors, all the way out to the very edge of the observable universe.
Okay, let's dive into this. Here is our flight plan. 1. Leaving Earth behind. 2. Orbiting our home planet. 3. The new lunar era. 4. Mars and the asteroids. And finally, 5. Peering into deep space.
All right, Phase 1. Leaving Earth behind. The rockets making space accessible.
Every great journey to the stars obviously has to begin on the ground. Breaking Earth's gravity well is arguably the hardest part of space exploration. It requires staggering heavy lift rockets and private engineering feats that are just completely reshaping our access to the cosmos. Just look at the sheer pace and global scale of these recent milestones. On July 24th, SpaceX captured stunning footage of their Starship upper stage making a soft ocean landing after its 13th test flight. Then, barely days later in late July, Skyroot successfully launched India's very first private rocket, which goes to show how commercial access is expanding globally. And looking ahead to late August, NASA has already begun fueling the Roman Space Telescope for its upcoming launch. We are rapidly paving a multi-lane highway to space.
Moving on to Phase 2. Orbiting our home planet. Living and working in low Earth orbit.
Once we break gravity, we arrive in low Earth orbit, or LEO. This is basically our orbital backyard, a place where human endurance, international cooperation, and advanced manufacturing are being fundamentally put to the test every single day. To really grasp the scale of what we do up there, wrap your head around this number: 12 million kilometers. The Indian Space Research Organization recently reported on the successful conclusion of the Axiom 4 mission. During that mission, the crew traversed roughly 12 million kilometers, completing a staggering 282 orbits aboard the International Space Station, all while conducting vital microgravity experiments. To put that into perspective, that is the equivalent of traveling to the moon and back over 15 times.
And this brilliantly illustrates how we're preparing to stay out there even longer. The European Space Agency, teaming up with Airbus, successfully operated the first metal 3D printer in space, creating an actual metal product right there on the ISS. Now, why does this matter? Well, think about it. If a tool breaks on a 3-year mission to Mars, you can't just order a replacement from Earth, right? You have to make it. This is a massive, tangible step toward total crew autonomy for long-duration missions.
Next up, Phase 3. The new lunar era. Returning to our nearest neighbor. So we're leaving Earth's orbit and heading to our nearest celestial neighbor. But as we look at the moon today, it's vital to differentiate between our historic legacy and our future. On one hand, we have confirmed history. We know the triumphs of Apollo 11, and we know that on August 2nd, 1971, the Apollo 15 mission executed the very first televised liftoff from the lunar surface. Those are absolute facts. On the other hand, we have future mission concepts, like NASA JPL's Promise, which is a concept for a nuclear-powered lunar rover designed to survive the brutal lunar night. We're not saying any specific future outcome is guaranteed here, but it's fascinating to see how the verified facts of the Apollo era are serving as the foundational bedrock for these theoretical future architectures.
Let's see how this builds our momentum outward. 406,771 kilometers. That is the maximum trajectory distance reached by the Artemis 2 crew, officially making them the humans who have traveled furthest from Earth in history. They completely smashed the previous distance record set by the legendary Apollo 13 astronauts back in 1970 by over 6,000 kilometers. The sheer audacity of returning humans to deep lunar space is just awe-inspiring.
All right, Phase 4. Mars and the asteroids. Expanding our robotic frontier. We're going to leave human spaceflight behind, just for now, and transition to our robotic frontier. Out here, millions of miles away, autonomous rovers and probes are doing the incredibly heavy lifting of deep space exploration on our behalf. Take NASA's Curiosity rover. Even after years and years on the red planet, it is still rewriting our geological textbooks. Recently, Curiosity discovered a field of entirely unique honeycomb textures on the Martian surface. It's a fantastic reminder that no matter how much we think we know about our planetary neighbors, the hard, confirmed science coming back from these rovers always finds a way to surprise us with complex new mysteries. And right in that same neighborhood, we have NASA's Psyche probe. Psyche recently executed a flyby of Mars, coming within 4,500 kilometers of the planet. So the crucial point is that this wasn't just some quick sightseeing tour. They used Mars for a gravitational slingshot to speed toward their ultimate destination, the metal-rich asteroid 16 Psyche. But on the fly, they fired up their multispectral imagers to capture thousands of observations, specifically hunting for a faint, dusty ring around Mars and tiny undiscovered satellites, or moonlets. I mean, talk about a masterclass in multipurpose orbital mechanics. Finally, Phase 5, peering into deep space. Telescopes unveiling the early universe.
We are now leaving the solar system entirely. We're traveling not with physical probes, but with light. Through the lenses of our most advanced space telescopes, we are gazing into the deepest, darkest edges of the observable universe. And the synergy here is incredible. Hubble unexpectedly caught comet K1 fragmenting into at least 4 pieces as it left our solar system. That is a minuscule statistical probability to witness. Then, using archival Hubble data combined with supportive observations from the James Webb Space Telescope, astronomers finally located the first missing stellar mass black hole in the massive Omega Centauri star cluster. And perhaps most mind-bending of all, Hubble recently detailed a fascinating early galaxy known as MXDF Z4.4. To give you an idea of what that means, the European Space Agency described the discovery as finding ultraviolet light from a galaxy that existed just 1.4 billion years after the Big Bang. Just think about that staggering scale of time for a second. This galaxy contains tightly clustered young stars producing ionizing light that is actually transforming the opaque gas around it. It suggests that pioneer galaxies exactly like this one were responsible for clearing the dense, neutral fog of hydrogen gas that once choked the early cosmos. We are literally watching the universe turn its lights on.
Which brings us to the end of our outward journey today, and it really leaves a question I want burning in your mind. As our telescopes pierce that neutral fog of the early universe, as Webb, Hubble, and soon the Roman Space Telescope look deeper than human eyes ever have before, what new mysteries are waiting for us in the dark? The footprint of our knowledge is expanding every single day, and frankly, I cannot wait to see what we stumble into next.